भूल गए?
Did a few, sir.
Did a few. देख के बताइए जरा नोटबुक में कौन कौन सा किया आपने। अबीर, अस्सलाम वालेकुम, हाउ आर यू?
Walaikum assalam, sir. I'm good. What about you?
I'm good. So did you try these questions?
No, sir.
अरे ऐसे कैसे चलेगा, आप पढ़ ही नहीं रहे हैं। What about Faisal? Did you try Faisal?
No, sir.
Why? What happened?
Sir,
Forgot.
I forgot. Yeah.
तो उसी दिन कर लिया कीजिए। The only thing is that एक ही उसका उपाय है ना, आप उसी दिन कर लिया कीजिए, भूल जाइए। And also forgot का मतलब you did not even flip the pages of notebook, right? You did not study chemistry, I think then.
No, sir.
No, you did not study chemistry. That hurts. Sir, Fatima, you tell me, कितना किया आपने इसमें से? 13.9. Did some ना? कुछ नहीं किया, ऐसे बोल दिया फातिमा ने। Yes, Fatima? What happened?
Sir.
नहीं किया आपने ना, ठीक है, आपकी आवाज
Sir, I
से लग
did
रहा है।
3 of them.
3 of them. Which ones? Tell me. तीन किया आपने ना, तो हाँ ठीक तो है, तीन ही तो, तीन, हाँ ठीक
The
है।
6th one.
6th one. Okay.
And the 3rd one. And the first one, just the A and B.
B and first
B.
one. B तो नहीं है ना, 13.9. Okay. So 6th one. C6H5 NO2 in the presence of Fe and HCl. What will I get here, guys? Fe and HCl. NO2 will be converted into NH2. है ना? NO2 will be converted into NH2. You will get C6H5 NH2. Okay. After that, we are reacting this with HNO2. So if you remember HNO2, it is ONO. HNO2 is what? ONO. So when we react ONO, what we get? We get benzene, disonium. What do we get? We get benzene, disonium, salt. So you will get C6H5 and 2 plus Cl negative. Please remember this ONO, it is coming from HCl plus NaNO2 na. So ये याद रखिएगा. That is why this Cl is coming from that HCl. So we don't have HNO2 that is prepared like very बहुत पहले से. You have to prepare it on the spot. You have to prepare it. Freshly prepared HNO2 is required. So we'll get the benzene disonium chloride, and after that we have C6H5OH. ठीक है, तो ये रिएक्शन आपको नहीं आता होगा because this is from the reaction of benzene disonium chloride and it is not there in your syllabus. Okay, so till here at least you would have done. Then you have third reaction, but if you react this, you will be getting structure which is like this. You have C6H5, then there is N, double bond N, and then again when you react C6H5OH, this just adds on. So instead of chlorine, you have the phene group, that is the phenyl group, and OH. So you get this product. Otherwise, this reaction is not there in the syllabus. Okay, so you had to do till here at least. Then let us see the third one. Third one is bromoethane. We have CH3, CH2, Br. First reaction is KCN. So I hope you remember this reaction. This will add one carbon atom, CH3, CH2, Cn. Further, there is a reduction, LiAlH4. LiAlH4. So we are going to add hydrogen on carbon and hydrogen on nitrogen also. So we'll get CH3, CH2. This carbon will also get CH2. This nitrogen will also get NH2. So this is the final product in the third reaction. Next is which one? First reaction that you did. Fatima, you please check. Okay, so CH3, CH2. Okay, similar problem. CH3, CH2 iodine in the presence of NaCN. So NaCN or KCN, both are quite similar. You will have CH3, CH2, and then CN. Further, what are we doing here? Partial hydrolysis of OH negative in the presence of a base, OH negative. They are saying partial hydrolysis. Okay, partial hydrolysis. So what is going to happen? You will add water. So how will you add water? You will add the two hydrogens in the nitrogen and oxygen to the carbon atom. You will get CH3, CH2, C double bond O, NH2. That is a amide. That is amide. What is next? NaOH in the presence of Br2. Now, can you NaOH plus Br2? Bataiye. Which reaction is this? This reagent is of which reaction? ये देख के आपको बता देना चाहिए. Br देख के बताइए. And then you have amide group. नहीं. Hoffman bromamide degradation. Hoffman bromamide degradation. So Hoffman bromamide degradation में you will have bromine atom and there will be a amide. So what is going to happen here? You are going to get a amine from the preparation of amine. Na, it is you are going to get a amine, but it will have one carbon less. So you have two carbons. How many carbons did I make? One, two, three carbons. Now, so one carbon less. You will get CH3, CH2, NH2. Okay. Next, what other reaction? Okay, did anyone else try this? Amalia Ahmad 13.9.
No, sir.
No. Why? What are you guys doing then?
Yes, sir.
क्या पढ़ रहे हो आप लोग?
Sir,
अच्छा, Amalia, you
complete
did try.
project.
अच्छा, wait. Amalia, any doubt in any of the questions? In 13.9?
The sixth question.
Sixth question, na? Okay, I think sixth question you will have doubt after this part, right? After making the benzene disonium chloride. Right, Amalia?
Yes, sir.
So after that, you don't have to do, because this reaction here, that is the reaction of benzene disonium chloride, benzene disonium salt. It is not there in the syllabus. So just had to make till benzene disonium chloride because we had till here. This is one of the reactions of amine. Okay, so we don't have to do any further reaction of C6H5OH, that is with phenol. You will be getting this product, but again, not in syllabus. Okay, this is not in syllabus. I hope they adhere to whatever syllabus they have given and they don't give you these type of questions. Okay, chalo. Any other question, Amalya? I think all the others were fine, which is with Thani or
Yes, sir. No doubt.
no doubt. No? Okay, fine. Chalo. Moving to the next chapter, that is D and F block. By the way, what are your school teachers saying about the result? Do they have any
No
new?
idea. No, sir.
No one has any idea. I don't know why.
So board results,
Yeah, term one.
it will not, they will not
They will not publish it.
give the result. No,
They will not give the result. मतलब कभी नहीं देंगे क्या?
they will combine the result with second term and they'll give all together.
हाँ. Where did you get this news?
So actually this one a topper of our school gave.
Oh my God. Topper of your school gave this. Okay. Did he source anything? Yeah.
Sir,
so-
afwa. Sir, it's
Why?
called
He's every
afwa.
time on the CBSE website. every time is there inside.
He may be in the CBSE website link, but CBSE website doesn't say this, no. CBSE results.nic.in, it doesn't have anything like this in there. Okay. There is nothing news related to exam. This is also an old notice. Let me see, what is this? This must be regarding your term 2. Term 2 bhi aapka, okay, fine. This is 31/12/2020. Okay, this is 2020. ये तो बहुत पुराना है. There's no news in the CBSE website. Okay. Moving on to the next chapter, that is D block elements. How was your term 1 paper, by the way, Faisal? What?
So it was good.
It was good. What did you find tough? Like, which?
So nothing.
Nothing tough. आप ही हैं क्या topper?
No, sir. Because the paper was like it was easy. Only the chemistry and computer paper was easy. Rest all of them were hard.
अच्छा, वही तो हम पूछ रहे थे. Like, I was asking about the other papers also. Chemistry, I know. Chemistry was easy. I saw the paper. What about others? Physics, maths, कैसा गया था आपका?
It was bad.
Time.
The question was also like very tough.
Tough या lengthy? यही है मतलब, like, sometimes students confuse with this. Tough या lengthy?
So lengthy also tough also both.
Also tough also. Fine. Chemistry is, I hope chemistry is also going to be easy in the term 2 also, because अच्छे खासे portion हटा दिए इन लोगों ने. खैर, D block elements. Okay, so in D block element, what are the D block elements? First of all, how will you define a D block element? So all those elements in which the last electron, it goes to the D subshell. Those elements, in which last electron goes to the D subshell. D subshell. अगर ऐसे आपको आगे लिखने के लिए, then I'm giving you a very nice word in English, goes to the D subshell of penultimate shell. Penultimate shell. So penultimate means second last. Okay. Penultimate means second last. That means if you have four shell, so it will be going to the 3D subshell. Okay. If you have 5 shells, then it will be going to the 4D subshell. So you please remember this. Those elements in which last electron goes to the D subshell of the penultimate shell. D subshell of the penultimate shell. Now the next word that you have are the D block elements. Are D block elements. D block elements. Okay. Next is a word which is known as transition elements. Transition elements. Okay. Now transition element has a definition which you should remember. That is, so all the D block elements, they cannot be classified as the transition elements. So these elements are the elements of D block. The elements of D block you can say which has incomplete D subshell, which has incomplete D subshell. Now there are two different types of, I can say, 2 different types of atoms. You can either have the incomplete D subshell in the natural form, in its ground state. Okay, the D subshell in ground state, or in any one of their oxidation state. Okay, so there is two things which is very important. There should be incomplete d subshell. Okay, there should be incomplete d subshell. Okay, incomplete d subshell. Then the next thing is, where should be the incomplete d subshell? Either in the ground state. Ground state means where you have not lost any electrons. Now, since all of these are metals, they have a tendency to lose electrons. That is why they will be having a positive oxidation state. Now, in any of those positive oxidation state, if the d subshell is incomplete, then also it is known as, it will be known as a transition element in any one of their oxidation state. Okay. Now, I'm going to give you some examples here. You will write the electronic configuration of them. Okay, and then classify, tell me whether it is transition element or not transition element. Okay, so identify, write the electronic configuration. And identify transition element. Okay, number one. Let us take Cr, chromium, which is 24 atomic numbers, copper 29, zinc 30, Fe 26. ठीक है? Write the electronic configuration.
Yes, sir.
And all of you, what about others? Guys, so for chromium, we'll start with the noble gas, that is argon,
AR
Ar, and after that
4s2 3d
4s2 3d
3d4.
3d4. How many of you have got this? Please raise your hand. What about Fatima? Fatima, you did not get this? Fatima, are you there? Abir, what happened? You did not write the electronic configuration?
Sir, I
हाँ,
wrote
very good.
3d6.
3d6 लिख दिया आपने? 3d6 कैसे हो गया आपका?
Sir,
ये तो गलत है. Okay, this is wrong.
yes, sir.
First thing first. This is wrong. 4s2 3d4 is wrong. Why it is wrong? Faisal, you tell me. It is wrong. I'm saying. आपको याद आ जाएगा. बताइए किस लिए गलत है? Yes, Faisal.
Sir, why it is wrong?
You tell me why it is wrong.
1:2:2p6 3:3p6 4
नहीं वैसे नहीं होगा, कुछ और है. There's some other reason. 11th standard याद कीजिए. Chapter 2 11th standard. Extra stability of
Exception
stability of
4s1 3d5.
4s1 3d5. Correct. Fatma got it right. Yes or no? Faisal याद आया? Sania, Amalya, all of you guys remember this? Yes or no? Tell me.
Yes, sir.
Yes, sir.
Similarly, in copper also it will be argon 4s1 3d10. Correct?
Yes, sir.
Right? So copper and chromium, these are exceptions. Why? Because half-filled and fully filled D subshells are more stable. Now for zinc, it will be argon 4s2 3d10, and in iron it will be argon 4s2
3d6.
4s2 3d6. Okay, argon 4s2 3d6. Okay. Next thing is, if you see, like, look at the first time, then you will say that we have chromium. It is a transition metal.
Transition.
Copper, you will be seeing that it is not transition metal because it is having complete D
3D
subshell, right?
Yes.
But please remember, and in any one of their oxidation states. So copper 2+, but Cu2+, electronic configuration will be argon, and there will be 3d9, 4s0 and 3d9, right? Because first electron will be from the S subshell because it is the outermost. This is the outermost subshell, right? Outermost shell, fourth shell, and then 3 is inside. So you'll have 4s0, 3d9. So you can see here in its common oxidation state, that is +2, it has a incomplete D subshell. But that is not true in zinc, because even if I take zinc 2+, then I will be having argon, and there will be the 2 electrons from 4s will be leaving the atom of zinc, but this 3d10 will be intact. Now you can see that zinc in its ground state as well as excited state has the complete D subshell. That is why zinc is not a transition metal, Now iron, it is obviously a transition of, you can see here 3d6 incomplete. Okay. Now I am going to write here, write a note that coinage elements, coinage metals. What are coinage metals? Copper, and what else? Silver
Gold.
and gold. These are the coinage metals. So all of them now, they will be having 3d9 electrons. Sorry, 3d10 electrons. That is, they will be an exception in 4s1, but still they will be considered as a transition element. Coinage metals are included in transition elements, even though they have D10 in their ground state, because in their +2 state they have D9, which is incomplete D subshell, Next is the last element of, that is zinc, cadmium, and mercury. ZnCdHg. ZnCdHg. These do not have incomplete D subshells. In their ground state, as well as ground state as well as in their common oxidation state. Hence, they are not transition elements. Okay. Please write this down. Have you guys written the above part? These 2 points?
Yes, sir.
Okay. So write the note. Let me know if you're done. Okay, Abir is done. Okay. Waiting for Amalya and Faisal. Please let me know. Raise your hand if you're done. Okay.
So done.
Done. Okay. Thank you. What about Ahmed? Done? Yes, Ahmed. Ahmed and Amalya. Okay.
Yes, sir.
Okay. Others you can write. There are 4 transition. You can write that. The D block elements are spread. The D block elements are spread in different series. Series of transition. Different series of transition elements. The first is first transition series. First transition series. Okay. TSS transition series, or it is also known as or 3D series. Why 3D series? Because in this series of elements, what is happening? The electrons, the last electron, they are getting filled up in the 3D subshell. They are getting filled up in the 3D subshell. So it starts with the atomic number 21 that relates to scandium and to zinc, that is 30. Okay. Second is second transition series or the 4D series. So the 4D series will start with ytterbium 39 to cadmium 48. The third transition series or the 5D series, which is spread across 57, start with 57 lanthanum. Then there are a series of F block elements. And after filling the 14 F block elements, we go till mercury, that is 80 Hg. Okay. Next is the fourth transition series. That is the fourth transition series or 6D series. It will start with actinium. It will start with actinium. So it will be 80 plus 57 and 89. 89 actinium. 2. You have at least, I think we have got new metals now, 112. I think 112. So whatever the name it will be for 112, what will be the name for 112? Un something, right? UUB. Okay, according to the IUPAC nomenclature, okay, conventions of IUPAC nomenclature. I don't know whether it has been given any particular specific name. Okay, I don't know whether the voting has been done or not. But if I follow the IUPAC convention, it will be un by right? You have this in 11th standard, na?
Yes,
Yeah.
Okay. Now, in this, we have to mostly learn about the first 3 transition series. So we'll be talking about mostly about the first 3 transition series. Okay. Now, because the 4th transition series is quite new and the chemistry of 4th transition series is not much known. It is not much known. Okay. Now, starting with the general characteristic. Okay. Now, general characteristics of the D block elements. So listen very carefully. The first is atomic radii. Okay, so atomic radii. Let us write first thing, that is how it relates to the S block and P block elements. So the atomic radii of the transition elements, these are smaller than S block, but larger than P block. So you can see it is one of those things. Like for example, atomic radii, it transitions through the transition elements. So it transitions through the D block element. That is why also these are known as effectively known as transition elements. It is smaller than the S block, but larger than P block. So it is intermediary. It is intermediate between S and P block elements. So this is in relation to the different blocks. Now let us look at inside the D block how the different elements of D block they behave. If I go from left to right in the period and then top to bottom. So when we go left to right in a period, okay, when we go left to right in a period, that means I am moving through a transition series. So in a transition series, what happens initially as the atomic number will increase? If I go from scandium to zinc in a transition series, as the atomic number increases, first thing that happens is the atomic radii decreases. As the atomic number increases, the atomic radii decreases. Okay, atomic radii decreases around till the middle. Like if I reach the 5th or 6th element of the transition series, it is like till that middle, it is decreasing. Then in the middle, it gets constant. Then becomes constant. Then at the end, it increases. Then at the end, it increases. Then it increases. towards the end. It increases towards the end. Okay. Now, I have written it in this way because I also want to give the reasons here. Okay. So first thing first, the atomic radii initially it decreases. Why does it decrease? Then why does it become constant? And then why it increases at the end? Why it increases at the end? Okay. So these are the three things that is happening, and we will explain all of these things. So first thing is that why the atomic radius decreases, because as I increase the atomic number, so what I am doing, I'm increasing the atomic number, right? Now, if I'm increasing the atomic number, then the number of protons and number of electrons both are increasing, and that is why the effective nuclear charge increases. Now, if I have more protons, then it is going to attract the electrons more effectively, and the size will shrink. The size will go small. So that is why initially what happens, there is an increase due to increase in Z effective, yes or no? Effective nuclear charge due to increase in effective nuclear charge due to increase in effective nuclear charge. Okay, first reason is this. Next is, then why does it become constant? Why does it become constant? Now, when I'm increasing the number of protons and the number of electrons are also increasing. So number of electrons are increasing in the, let us say, the 3D subshell. Now, when the electrons are increasing, what is happening? They are also increasing the screening effect. So two things are happening here. There are two things which is happening. I'm increasing the number of proton. So if the number of proton will increase, then tell me attraction will increase or decrease? If I increase the number of if I increase the number of proton, the atomic number increases, then what will happen? Attraction will increase or decrease?
Increase.
Attraction will increase. Now, if I am since I am also adding more and more electrons, then the screening effect, that means what is it is doing? It is shielding the pull of the nucleus. So when I add more electrons, what is going to happen? The attraction will decrease, yes or no? Because of screening effect.
Yes, sir.
Because please remember, we are adding in the 3D subshell. The outermost subshell will be the 4s. Nothing is happening here. So when I'm increasing the electrons inside, then these electrons are acting as these are acting as a shielding elements, and they are shielding the 4s2 electrons. So then it becomes constant. That means the two effects that we have, they level out. The two effects, that is the increase in the atomic number, that is increase in the Z effective, and the screening effect. So both increases, and that is why what is happening, it counterbalances. So then it becomes constant. Why? Because due to counterbalancing, to counterbalance of Z effective by shielding. By shielding of electrons in D subshell. Okay, by shielding of electrons in D subshell, because we are adding more and more electron. Now, at last, then it increases towards the end. So the reason for this increase is that when we have these electrons, they start to have repulsion, and when there is repulsion, they will move far apart. And if they move far apart, the atomic radius, it will increase. The atomic radius will increase. So then it increases towards the end due to interelectronic repulsion in D subshell. Okay, in D subshell. So these are the three trends and the reason also. And the reason is also there. So this is happening, all of this is happening when we are moving in a transition series. So we are moving along a period in the D block elements in transition series. Okay, in a transition series. Okay, so please write this down. I think you have written or something. Let me know if you have...
little right.
Yeah, I will just scroll, zoom out a bit. I think now it is visible for all of you. Done, guys? Done, everyone, right?
Yes, sir.
Abir is
Yes, sir.
done. Okay, fine. Now, next is what is going to happen when I go down the group. So the atomic radii increases down the group. Okay, increases down the group. So obviously this reason is very much obvious that if I go down the group, then I'm increasing the number of shells. So as I go from first, second, third, fourth, fifth, sixth shell, then obviously the atomic radius is going to increase if I go down the group. Okay. But important point to note down here is we have the first transition series. Okay, so it is smaller than the second transition series. Okay, so we are talking about here atomic radii. Okay, the property that we are mentioning, first transition series elements, these have smaller atomic radii than the second transition series elements. But when I look at the second transition series and I compare this to the third, then obviously the third is greater, but it is quite like very, the difference between the second and third is very, very, very less. So you can say that they are almost equal. Okay, they are approximately equal. They're approximately equal. Here also we are talking about the atomic radii. So there was an increase if I go from second to the third transition series because I'm going down the group, but the increase is not well defined. The increase is not well defined. What is the reason for this? So please write. So please write here. This wait a second. Let me write it like this. The atomic radii of third transition series is almost similar to that of second transition series. This is due to the intervention of 4f orbitals. 4f orbitals which are filled before 5d subshell. And since 4f electrons have very low shielding effect, the nucleus attracts the electron effectively which leads to small size. That is why now the 3D transition series, it is the 5D series, right? This is the first is the 3D, second is 4D, third is the 5D series, and before 5D subshell, we have to fill the 4f electron. And these 4f electrons, they are not very good at shielding. That is why the electrons that is in the outermost shell, they are easily attracted. They are easily attracted by the nucleus. And if it is easily attracted by the nucleus, the size is going to get small. Okay, so the size is going to be small. That is why the second transition series and the third transition series, they have almost similar atomic sizes. Okay, but in general, it increases If I go down the group, okay. So please write this down. Let me know if you're done. One more thing, this phenomena is known as Lanthanide contraction. This phenomena is known as Lanthanide contraction. So if they ask you what is Lanthanide contraction, you are going to write this whole thing. The atomic from here, the atomic radii of third transition series is almost similar to that of this much. This is the reason, and this phenomenon is known as Lanthanide contraction. Write this down. Let me know if you're done. Okay, Amalya is done.
Yes, sir.
Okay, everyone is done. Just let me know if I have to scroll up or something. Okay. So we learned about atomic radii. Next thing is ionic radii. Ionic radii. Okay. So it follows a similar trend. It follows the same trend as the atomic radii. But what about if I have different types of ions? Some ions may be +1, +2, +3. So you can say that the ionic can write like this. The ionic radii it will decrease with increase in oxidation state. Okay, that means if you have metal +1, this will be bigger than if you have the same metal with the +2 oxidation state. If you have the same metal with +3 oxidation state. Okay, this is the meaning. The ionic radii decreases with the increase in oxidation state, because if you are decreasing the number of electrons, so there is less electron that has to be attracted. So the attraction from the nucleus is going to be more and more effective, and that is why the size it shrinks. But if I talk about for same oxidation state, the same oxidation state, the ionic radii decreases with increase in nuclear charge. Nuclear charge means atomic number. Nuclear charge. Nuclear charge. What is nuclear charge? Number of protons. Number of protons is determined by the atomic number only. Okay. So this is about atomic radii. This is one of the important points. This is important, that the ionic radii decreases with increase in the oxidation state. Write this down. Let me know if you're done.
So what is M?
Metal, any metal. Okay, if the metals, these are same metals only. For example, if you do CO +1, +2, +3, then I'm comparing those type of metals. M is any metal. Got it, Faisal?
Yes, sir.
Okay. Then guys, all of you.
Yes, sir.
Next is the ionization enthalpy. Delta H ionization standard. Okay. Delta H ionization enthalpy. So a few trends are observed. So I will write those trends. We will first of all start with the comparison with S and P block elements. How is the ionization enthalpy if I compare that with S and P block elements? So please write the first, write A part. Okay. Now we all know that if I have a metal and it is going to give me M plus 1 electron, it is known as the first delta Hi, the first ionization enthalpy. But if I take M plus and then I remove an electron, getting M2 plus 1 electron, this is known as the second ionization enthalpy. Right, guys? You know these terminologies: first ionization enthalpy, second ionization enthalpy. Yes or no? You remember from 11th standard? Okay, fine. So when we compare the first ionization enthalpies of D block elements with S and P block, what do we see? We see that these are higher than S but lower than. First delta Hi of D block is higher than S block, but lower than P block. Why is that? See, when we have S block elements, but it is lower than that of P block elements. So when we are going to remove an electron from the S subshell, it is going to be difficult, right? But when we are going to remove from the P, it is going to be a bit more different. It is higher than the S block elements. Please write C here. The increase in delta Hi from S block to D block, when we are removing electrons from the S block and the D block. Okay, S block to D block is due to increase in nuclear charge. Increase in nuclear charge and the increase in nuclear charge and the less shielding effect of D subshell. Okay, so one more thing you have to remember, which electrons are removed when we are removing electrons from the when we are removing the electrons from D block, it is the S subshell electrons are getting removed. For example, if I have, let us say, copper. So copper is argon 4s1 3d10. So in this you can see that 4s, it is the outermost electron. That is why this 4s electron is going to be removed. This 4s electron is going to remove. And before the 4s, we have the 3d. 3d is inside. Okay. These are two different things. These are all, we have written this 4s and 3d in terms of their energy. But when I look at the atom, 1, 2, 3, and then 4. So the 4s electrons are here and the d electrons are here. Okay. The third shell. So we are going to remove the electron from the fourth shell. Inside that we have the 3d electrons, and this 3d electrons, they have lower shielding than that of SNP. Okay, that is why if I compare two things here, let me show you. Calcium. So calcium is argon 4s, how much? 2. Okay, then we have scandium, Saktina. Yeah, this is argon 3d1 4s2. Okay, now here this 4s2 electrons, these are shielded by the argon. That is, what is this? Argon, it has S and P. And here we have 3D. Okay, these are 3D subshell electrons. So we have more and more electrons here. That is why it is difficult to remove the electrons. That is difficult to remove the electrons. Okay. And the, okay, let me write shielding of the D subshell. Shielding of the D subshell. This increase in the delta HI from S block to D block is due to the, this is the main reason, increase in the nuclear charge and then the shielding effect of the D subshell. Next is why it is lower than that of P block elements. Tell me. Again, when I go from D to P, what is happening? We are increasing the electrons. Sorry, we are increasing the atomic number or decreasing the atomic number?
Increasing.
Increasing the atomic number. So then protons will increase or decrease?
Increase.
If the proton is going to increase, then the attraction is also increased, yes or no?
Yes, sir.
Now, if the attraction is increased, then what is going to happen? We will be requiring more and more energy to remove the electrons, right?
Yes, sir.
Okay. So we can write here that the nuclear charge increases as we move from D to P block in a period and hence the delta HI of D is lower than P block. It is lower than P block elements. Okay. Write this down. Let me know if you're done.
Yes, sir.
No, sir, just a second.
I'm waiting.
Done, sir.
Everyone done? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Let me just get the values here, the data values. Then we will talk about the trend. Not here. Okay. Clear, no? Okay. Then first of all, tell me what series is this? First transition series, second transition series, or third transition series?
First transition series.
First transition series, and the 3D series. Okay, so in that we are going to look at the first ionization enthalpy of different elements. Okay, of different elements. So our idea, first of all, is that when we go from scandium to zinc, what is going to happen? The atomic number is going to increase, the effective nuclear charge is going to increase. So we are expecting that there should be a gradual increase in delta HI. Okay. Our reason is what? Our reason, no, if there is any other, whatever we have expected, that means increase in delta HI, it is not present, then we will look for a reason. Now, first of all, tell me, when I go from scandium to titanium, is there an increase or no?
Yes, sir.
Okay. What about if I go from titanium to vanadium?
Yes, sir.
Decrease.
There is a decrease, right? So we'll have to explain this part here. Okay, then now next, tell me, increase or decrease?
Increase.
Increase.
Increase, okay, fine, but still it is less than titanium, है ना? So chromium, it is what? It is less than titanium. That is not also logic. That is also not logical. But when I go from chromium to manganese, increase or decrease?
Increases.
Increase.
Increases. Then increase or decrease?
Increase.
Decrease.
Increase. And then I go from,
Decrease.
Decrease.
now there
Yes.
is a decrease. Then
Again
Decrease.
Decrease.
again decreases, and then
Increase.
Decrease.
little bit increases.
it increases, and then
Increase.
Increases.
then increases. Okay, then increases. Now, when you look here, so most of the abnormality that we are looking is that when I am just around, right? Mn is the middle, right? 25. Yes or no? And when I
Yes,
move
sir.
towards the middle, it is going fine. Then I have some irregularity in this part from titanium to chromium, and then from iron to copper, and then we have iron to copper. Now we have to look at why is there any abnormality? Okay, why is there any abnormality here? Okay. The first thing that I will write here, in general. Now, how do we predict in general? Na? As in general, you see like this. You start here, you look at the scandium, okay, and then you look at zinc. You see that there is an increase, right? There is an increase like this. So you say that in general, the delta, the first delta HI, the first delta HI of B block elements in a series increases as we move in a transition series. As we move in a transition series. Now, whatever anomaly that you see here, that is due to a phenomena which is known as the reorganization energy. Okay, as we move near the middle, or middle means half filled, deception. As we move near the middle, that is the half filled deception. There is a reorganization energy accompanied by ionization. Okay, it is accompanied by ionization with some increase in exchange energy. So exchange energy is those energy that is related with the half filled and the fully filled subshell. Exchange energy with some increase in the exchange energy in DN configurations. DN configurations. Okay. Now the reason that you see here is if I go from, this is 23, right? This is 23. Now if I remove one electron, then what it is going to happen? I will be having 1 electron in the s subshell, and there will be 3 electrons in the d subshell. Okay, so what happens? The s subshell and the d subshell, the electrons in the s1s and d3, they start to mingle. And that is why the electrons, these are spread around a very large area. That means in the s subshell also and the d subshell also. So as the exchange energy increases, it is getting more and more stable. Okay, it is getting more and more stable, and that is why it is easier to remove electrons. It is easier to remove electrons from 56, then from titanium to vanadium, and then from chromium. Now, when I go from chromium to manganese, there is S1 and there is D5. S1 and then there is D5. Okay. Now, in manganese, you can see I had initially S2, which was fully filled, and now I have a half-filled subshell. So that is why it is getting unstable. It was completely stable right now because it is fully filled. This is half-filled. So this is a very stable system. Now, if I remove 1 electron from the S subshell, we have an unstable system. That is why this delta Hi is larger. Then again, we see that there is a decrease. Because if I remove 1 electron from the Fe, it is going to be S1 and there will be D6. So now what happens? One of the electrons from the from the D, it shifts to S, making it S2 and D5. Okay, so that type of exchange energy is possible in Fe. That is why we see a decrease. Here. Okay, now you can see that 717, then we have 762, and then 758. Right, so this decrease is due to that. So most of the time, the decrease is due to the reorganization. This term here, that is reorganization energy. After the ionization, what happens? The electrons, they reorganize themselves in such a way that they have a stable system. Reorganization energy. It is accompanied by the ionization. Okay. Now you can see that it is quite a detailed thing here. So they will not directly ask this question, but they can ask what is the reason for the abnormality or the anomalies or the irregularity in the trend of the ionization enthalpy or the first ionization enthalpy of the D block elements. You will just write this statement as we move near the middle, that is half-filled D subshell. There is a reorganization energy accompanied by ionization with some increase in D exchange, in the exchange energy in the DN configuration. Okay, so please remember this word, reorganization energy. Okay, so basically what happens? The S and D subshells, the electrons in S and D, they start to mingle with each other, which gives them a large area to be around. So when you have electron that is negatively charged, so when charge is spread around a large area, that is going to be more stable. And that is why this is known as the reorganization energy. That means S electrons are moving to D, so there is some reorganization happening. Okay, so this is the reason of the abnormality that we see. Okay, please write this down. These 2 points, the general statement and the specific statement.
Yes, sir.
Then all of you, is there anyone who's still writing?
No, sir. Done.
Done. Okay. Now, one question that they ask from here is for copper. Okay. So if I see copper and manganese, okay, if I see copper and manganese, there is a huge difference, right? There is a huge difference. So this copper one is very, very small. It is even smaller than that of titanium. So why is that? So you can write that as a question. Sorry, copper near chromium, hai na? Yeah, chromium is very, very less than manganese. So you can write the question. Cr has a very low delta Hi. Okay, very low first delta Hi. Give reason. Okay, so for this, whenever they ask specific question with a particular element, you first of all will make a First of all, we'll write the electronic configuration. So chromium is argon with 4s1, 3d5. Okay. Then you will show the ionization. That means chromium, we are removing one electron, making it Cr positive plus one electron. Then you will show the electronic configuration of Cr positive, and you will show that it is argon. The electron from 4s1 has been removed. That is why we have 3d5. That is why we have 3d5. Now you can say that since removal of 4s1 electron from chromium leads to a stable half-filled electronic configuration of Cr positive, that is argon 3d5. Stable half-filled electronic configuration Cr positive, that is argon 3d5. The delta Hi is low. Okay. This is due to the formation of a stable configuration of half-filled subshell. Half-filled D subshell, we have low ionization enthalpy of chromium. Done.
Yes, sir.
Similarly, you can also ask, see, zinc has a very high 906. So that you can be asked why. Okay, similarly for copper also, if they ask now why it is so much low, then you are going to say that. So copper is also low because we are removing copper is how much? This is S1 D10. If I remove one electron from the S subshell, I will be getting completely filled, right? I will be getting completely filled D subshell. That is why it is lower. Okay, now why is zinc very high? Question would be, explain why zinc has high delta Hi. Okay, the reason will be since zinc has 4s2 3d10 stable electronic configuration. Stable electronic configuration and the removal of electron from 4s subshell is difficult. 4s subshell is difficult. Now, one more observation in the ionization enthalpy. If I go down the group, so if I go down the group, the expected was on moving down the group. So we had the expected order was the 3D series will have the 3D series. It will have the highest ionization enthalpy because these are smaller, followed by 3D, then 4D, and then 5D series, right? This was our expected, but the actual story is that the first ionization enthalpy of the 5D transition element, that means the 5D one, these are higher than those of 3D and 4D, okay, than those of 3D and 4D. So when I look in the first transition series, now, okay, let me see, this is what we had only, okay, fine. We had only scandium. Okay, fine, fine. Yeah. We can write here regarding the. Let me get you. So actual will be 5D is, I am not getting the data. 5D is greater than 3D and 4D. Okay, 5D is greater than 3D series and the 4D series is greater than 3D series and 4D, both of them. Okay, so you will get a question, why is that? So you'll write the answer, why is the question would be, why is the delta HI ionization enthalpy of 5D higher than 3D and 4D? Okay, 3D and 4D. So the reason is, we explained here now regarding the F subshell, intervention of F subshell electrons. This the 4F orbitals, 4F orbitals before the 5D. That is why they have very low shielding, right? They have very low shielding. If there is low shielding, then what will be there? Attraction will be very higher. If attraction is higher, the nucleus is attracting the electron more effectively, and hence it is more difficult to remove the electron. So due to the lower shielding effect, due to the lower shielding of 4F electrons in 5D series element, the attraction of nucleus on valence electron is high, which makes it difficult to remove electron, Okay, that's it. That is why the 5D are higher than 3D and 4D. So in 3D and 4D, we have S and P substances which are shielding, which has a greater shielding effect. The nuclear charge is low, the effective nuclear charge is low, there's less attraction, and if there is less attraction, it is going to be easier to remove the electrons. But 5D, it has a higher attraction, that is why it is difficult to remove electron. That is why the ionization enthalpy is higher. Please write this down. Let me know if you're done. And then we will discuss the other properties tomorrow.
Done, sir.
Done, all of you. Okay. Everyone done? Yes or no?
Yes, sir.